Welcome to this lesson. We will be looking at rates of change for differentiation and also looking at how to set up differential equations towards the end of this lesson. So stay tuned. All right, so have a look at this question. Determine the rate of change of the area A of a circle when the radius r is equal to 3 centimeters, given that the radius is changing at a rate of 5 centimeters per second. Now, in this question, whenever you see, you are going to be using your chain rule, okay? And whenever you see the rate of change, I want you to think of dy over dx. Gradient, you know the rate of change, yeah, is your gradient. When we first started looking at differentiation, we spoke about the gradient of lines, the gradient of curves, all right? So when you read rate of change, I want you to think gradient, dy, dx, dA, dv, whatever it is, okay? That's rate of change. So what are we finding? If we read the first part, it says the rate of change of the area. So what is the area of a circle? Pi r squared. We are dealing with a circle, right? And we are finding the rate of change of A with respect to time. The rate of change of the area with respect to time. That's what we're looking for, all right? So ultimately, we will be finding this. But let's keep reading the question and see what else we have. We know that the radius r is, this rate of change that we are finding is when the radius r is 3 centimeters, right? Given that the radius is changing at a rate of 5 centimeters squared. So, the rate of change of the radius, this is writing dr with respect to time. The rate of change of the radius is 5 centimeters per second. That's the rate of change. That's what that sentence means. That the rate of change with respect to t, time. Let's actually go back to this where we have to find dA over dt. Now, if we use our chain rule, if you remember when we introduced the chain rule, and if not, obviously go back to the chain rule. The chain rule, we can get this dA over dt by having our dA here and our dt right there. And here will go something that we can cancel out so that these two merge together to give us this, isn't it? Yeah? So if you look at what we've been given, the extra that we have is a dr, because we've got dt covered already. So a dr will go here, and therefore a dr will go right there too. And these will cancel out, giving us dA over dt, right? So we know what dr over dt is. It is 5. So we can replace this with 5. We just need to find dA over dr, which we can get from here, because if we differentiate this, it's with respect to r. So therefore dA over dr will be 2 pi r. So now we can get that dA over dr to replace this, and we will be finding dA over dt. So let's put that in here. So 2 pi r. All right. Now, there's one unknown left, which is the r, and this is when we go back to this. It says, find the rate of change of the area with respect to time when r, the radius, is 3 centimeters. So when r is 3 centimeters, dA over dt, dA over dt, just write that nicely, will be 2 times pi times by 3, which is the radius, times by 5. And that simplifies to 1530 pi. So the rate of change of the area with respect to time is 30 pi. Let's have a look at this exam question. It's from the previous legacy paper, so we'll just use it because it's a good one. So first of all, rate of change will happen when something is changing its form. So the previous question was a circle, and the radius was changing, okay, as maybe it was expanding. And while it was expanding, the radius was getting bigger, and therefore, subsequently, the area was getting bigger, okay? And it will change every single second. The radius will change, and therefore the area will change. All right, what I'm going to do is I'm going to read this question twice. The first time, we're going to just do one nice reading of it, and then the second time, I will stop and emphasize particular parts and write down some of the things that we have, all right? So the figure 2 shows a right circular cylindrical metal rod, which is expanded as it is heated. After t seconds, the radius of the rod is x centimeters and the length of the rod is 5x centimeters. The cross-sectional area of the rod is increasing at a constant rate of 0.032 centimeters squared per second. Find dx over dt when the radius of the rod is 2 centimeters, giving your answer to free SF. And B, find the rate of increase of the volume of the rod when x is equal to 2. So let's write down some things that we know. We know we are dealing with this cylinder here. We are told that the radius is x. Okay, so radius is x centimeters and the length is it 5x centimeters. Yeah? All right. So what we're looking for, we're looking for part A, dx over dt. Right? So let's do what we did previously. Let's use our chain rule. So here we'll go dx and here we'll go dt. So here and here we will find something to use as a replacement. Okay? But let's read the question. Let's see what we have. It says, after t seconds, the length of the rod is 5. The cross-sectional area of the rod is increasing. So the cross-sectional area, which of this circle, is going to be A equal to pi times r squared, right? So pi r squared. But for r, they are using a x. So we don't want an r here, we want an x squared. So when we differentiate this, we have dA, we're differentiating with respect to x, yeah? So we're going to have what? 2 pi x. So now we can have our dA right here and our dA right here because they are going to cancel out eventually, giving us dx over dt. And if we want to have dx over dA, we can get it from here, okay? We have dA over dx, but dx over dA would be the reciprocal of that. It's going to be 1 over 2 pi x. Yeah? So dx over dA can be put in here as 1 over 2 pi x. So dA over dt, the rate of change of the area with respect to time, is given to us in the question as 0.032. So we can just simply write 0.032 in here. Now, when is this all happening? It tells us in the question, it is when the radius of the rod is 2 centimeters. So when the radius of the rod, which we're saying is x, is 2 centimeters, dx over dt will be 0.032, we'll just put this on the top here, over 2 times pi times by 2. So if you could just work this out on your calculators for me. 0.00255. And that's 2 free significant figures. That's your answer for part A. So for part B, what we're looking for, it says find the rate of increase of the volume of the rod. So the volume of this cylinder, let's first of all write down a formula for that. How do you find the volume of this? Area of the cross section times by the length. So the cross section is your pi x squared, which we use up here, times by your 5x, which is your length, yeah? To simplify this, we get 5 pi x cubed, and therefore dv over dx would be 15 pi x squared. Okay, so this is the rate of increase with respect to the radius. We want to find, what do we want to find? The rate of increase of the volume of the rod. So dv over dt. So we want dv here and dt there. We know that we are going to have dx and dx right there. Let me just get this out of the way. So we have dv over dx, which is 15 pi x squared. We have this from the previous question right there. Yeah, so dx over dt is in the previous question, so therefore 0.00255. And when is this all happening? It tells us in part B, it is when x is equal to 2. So therefore we are going to sub in x is equal to 2 in here. So 15 times by pi times by 2 squared. Let's just put this into a bracket for now. Okay, times by 0.00255. And the answer to this, please, on your calculators, 0.481 is our final answer. Okay, and this is volume, so you could write down the units, which is the rate of change in centimeter cubed per second. So 0.481 centimeter cubed per second. What we're doing, so can you see how important this chain rule is? Yeah, this is the thing that you need to understand. You need to be able to identify what you need, what you're given, what you can get from the question, and if necessary, sometimes you might need to find a reciprocal of something to get it in the form that you want it in, okay, that you're finding the question. So this is very, very important from the outset to have this written down. So you know what you need and what you don't need, and you can go and find it, either from the question or working things out yourself. Now this next question, you have a cube, and you're given the dimension of the cube, everything, all the lengths are x. Part A says that show that dv over dx is equal to 3x squared. So where do we get dv over dx from? It's from the differentiation of the volume. So for part A, if we know the volume of a cube, which is going to be length times base times width, okay, so here in this case it's going to be x cubed because all of them are x's. So the differentiation of v here would be dv over dx would be, to drop the 3 down, which is 3x squared, and that's part A done, yeah? For part B, it says given that the volume increases at a rate of 0.048. So it's given you what? It's given you the volume with a rate of increase with respect to t, yeah? So it's 0.048. What are we finding? Find dx over dt. So let's do this, dx over dt. And this is where you are going to apply your chain rule again. So here we'll go dx, here we'll go dt. Here and here you can work out it's going to be dv, so dv here and dv right there. Now dv over dt is right there, so you could replace this right now with 0.048. And what do we want? We want when x is 8. So let's just make a little note of that, when x equals 8. We want to find dx over dv. Well, if you look back at the previous question, we have dv over dx. So therefore, dx over dt can be found completely now by doing the reciprocal of this as 1 over 3x squared times by that value right there. And we can just substitute x as 8, and we can have the complete answer to dx over dt. And let's just put the 0.048 multiply over the top here, over 3 times by 8 squared. And if you can work that out on your calculators for me. So 0.0, how many zeros? 1, 2, 1 more 0, 2, 5. There you have it. Now let's look at part C of this question. So part C of this question says, find the rate of increase of the total surface area of the cube in centimeters squared per second when x is equal to 8. Right, the surface area is simply all the faces added up, right? One of those faces is x times x. So we've got 6 of them, so therefore the surface area, A, let's call it, is going to be 6x squared. So this is the surface area of the cube. What it's asking us for is dA with respect to time. Yeah? So let's put this in. So dA times by, over here, dt, and here will go what the thing that we need, okay? So if we differentiate this, what do we get? dA over dx, which is 12x. So clearly x is now in the picture, so therefore we're going to have dx here, and we're going to have dx there. Yeah? And that's how we can decide. Sometimes you can just wait, just hold back, leave this blank, and work on other things and see what comes out, okay? Right, so this is all happening when x is equal to 8, as the question says, yeah? We'll just put a line there. Right, dA over dx we can get from here, which is going to be 12x, times by dx over dt, which we got from the previous question, dx over dt, which is 0.00025. And now all we do is replace our x in here, so therefore 12 times by 8 times by 0.00025, and the answer is, please. And the answer is 0.024. There you go. So this is 9J. In this exercise 9J, there are some questions which ask you to set up differential equations, and we will look at differential equations properly in the integration chapter, but I just want to show you very quickly on how you can actually set it up. So you can actually start looking at some of these questions. So just have a quick read of this. It says liquid is pouring into a container at a constant rate of 45 centimeter cubed per second. At time t seconds, liquid is leaking from the container at a rate of 2/15 V, where V centimeter cubed is the volume of the liquid in the container at the time. Show that minus 15 dV/dt is equal to 2V minus 675. Now, what is setting up differential equations? Simply equations with differentiation in it. That's it. So let's have a look at this particular question right there. What do we have? We have liquid going into a container, right? So it's going into the container and it tells us that it's going in at a rate of 45 centimeters cubed, right? So the rate dV with respect to time is 45 centimeter cubed per second. Now, because it's going into the container, we are going to use the plus sign, because what's happening is there's also a leak on the container, and the leak, the rate that the leak is happening, so the volume is changing, right, with respect to time is 2/15 V. Now, because it's a leak, it's leaving the container, we're going to do what here? A minus sign. So in total, what we have, the total differentiation, the overall rate of change is going to be dV/dt. It's going to be 45, the rate that is going in, take away 2/15 V. Now we just have to show what they want us to show, which is to have that minus 15 there. So they have a minus 15 there. Well, simply just multiply by minus 15. So if you multiply this whole thing throughout by minus 15, well, you're going to have minus 15 here. So you get minus 15 dV/dt. And what's 45 times by minus 15? Minus 675. And then the minus and a minus here will be a positive, and it's a fraction. You're multiplying by 15, which would just leave us with a positive 2V. And then you can see now we've got what they want us to have, which is 2V positive first. So 2V minus 675. And there you have it. You've set up your differential equation there. On to the second example that I have for differential equations. You read this. A curve C has an equation y equals f of x, y is greater than 0. At any point P on the curve, the gradient of C is proportional. So let's start writing this down. So the gradient of C is proportional. Okay, now it's a gradient of C. So instead of writing a C, let's just write dy/dx. Okay, or you know, something in that form. They want dy/dx, so we'll actually use dy/dx actually. Okay, I was going to actually use something like, you know, dc over something. So at any point P on the curve, the gradient of C is proportional to the product of x and the y coordinates of P. So the x and the y coordinates of P, a product of it, which means they're multiplying. Okay, so this is what you have. The point A with coordinates 3, 3 is on C. So the point A with the coordinates 3, 3 is on C. And the gradient, so the dy/dx of this, of C is 1/6 at this point A. So show that dy/dx is equal to xy/54. Right, who remembers what to do with this proportional sign from GCSE? So replace it with dy/dx. We replace this with an equal k from GCSE, if you remember that, yeah? And then we've got that x and our y right there. So now we can start replacing things in here. So the dy/dx is going to be 1/6 here, is equal to k, which we will find what the value is, and the x and the y will be our 3 and our 3 here. So it's going to be k times 3 times by 3. So what does 3 times 3 give us here? 9. So we've got 9k. So we've got 1/6 is equal to 9k. To find what k is, we divide by 9. So therefore 1/6 divided by 9, which is 54. So therefore k is 1/54. And then we go back and we replace k in here. So therefore dy/dx will be equal to 1/54 times by x, y, and then you could just rewrite this xy on the top. So therefore xy/54. And that is your answer as they want you to show it. Hope you enjoyed this lesson, and I will see you in the next one.